Okay, so I'll record the rest of this lesson here so you guys can watch it again if you want to. Here's the reason why we have to have this whole lesson today. I threw the outcome that I'm supposed to teach you up at the top of this slide. I don't usually go through outcomes one by one, but this is something that you can and probably will get on the diploma. You need to be able to describe in general terms some of the physical, chemical, and technological processes. And then they give some examples: fractional distillation, solvent extraction, used to separate organic compounds from natural mixtures of solutions. So, I mean, if we're only focusing on the diploma, I can show you what the old diploma questions look like. Chances are they're going to give you a question where they're going to say, what sort of process would use the boiling point to separate different mixtures of crude oil? And you would say, fractional distillation. Okay, cool. Now that we've answered the diploma question, I don't know that really taught you anything though, right? Like I can tell you to expect a question. The answer is probably either fractional distillation or solvent extraction. So you need to know at a cursory level what some of these words mean. But my hope is that we can actually have a deeper understanding of what's actually going on. The whole point of this is kind of this first slide here. Crude oil in the ground is very raw and unrefined. And chemists have found a way to take that, first of all, to separate it, then to chemically react it, to hopefully turn it into something useful. Okay? Most of what it's used for, sure, gas, heating your homes. But I mean, plastics, those are useful. Medications, those are useful. So why don't we start with the first one? Fractional distillation. You probably, if you're in the textbook, found this page right here where, I mean, it literally defines this fractional distillation. It's right there written for you, right? So, I mean, what's happening? Well, as you look in the picture here, basically you're heating some crude oil. And as you heat the crude oil, based on the boiling point of the particular mixtures involved, the heavier stuff kind of settles towards the bottom. So that's like your asphalt, your wax, your lubricating oils. The lighter stuff, the gasoline, the liquefied petroleum, rises to the top. And basically it separates them based on boiling. Does that make sense? Okay, well, let's ask some deeper questions. What are the requirements in order to do so? And, you know, this is something that I actually did not, I mean, I've read this page 6 times at least, because I've taught this class 6 times. I learned something yesterday watching a YouTube video that I never clued in on before. And it's right here. Maybe you guys didn't catch this, because I didn't. It says, in the absence of air. Did you catch that little phrase right there? I didn't pick up on that until I watched a YouTube video yesterday. You guys were even here, as I was kind of catching up on just reminding myself of some of these processes. Why would this have to be in the absence of air? Also to combust. Yeah. I don't know that it actually mentions that, but that's something that I didn't realize. If you actually heat something up, but there's oxygen nearby, it'll combust it and turn it into CO2 and water vapor, which is not what we want to do, right? So when you actually heat this stuff up, it has to be without oxygen. Okay, another little note I have here on this. Why do they separate based on boiling point? Like, why do these things have different boiling points in the first place? And this page here, I mean, it does kind of continue going on here. It has an exclamation for boiling points. Essentially, once you get through the page break here, it comes down to London forces. Do you guys remember London forces previously? Basically, the long and short of it is that bigger molecules have more electrons, and more electrons have the ability to be temporarily on one side of the molecule versus the other, and it gives it more of a polar factor, more of a stickiness. So basically, bigger means better. So bigger means higher boiling points, more London forces. I thought this particular diagram, or what do you call this, a chart here actually, was kind of good to kind of point out. If you've got 1 to 5 carbon atoms, you're talking about things like methane, ethane, propane, butane. What do we use them for? Yeah, usually cooking or heating our homes. But as you've got like more carbon atoms, the temperature range seems to be going up. I didn't realize this until looking at this, but like asphalts and tars for roofing and painting, those are actually like the heaviest of all of the organic molecules. And when I start thinking about, especially like I've been bringing this up a few times, the big debate over fossil fuels and climate change, I don't usually think, when I'm thinking of fossil fuels, I don't think of roads as a benefit of what we're using our fossil fuels for. Does that make sense? Like whenever I hear someone talk about fossil fuels, I'm thinking burning stuff in our cars. But I didn't realize that like to make the roads with asphalt and pavement, we actually need fossil fuels for that. I didn't see this one before. Cosmetics. makeup actually requires the petrochemical industry? I never thought of that before. Right? I mean, I don't know that that's the most crucial thing to human survival, but if we had no oil, there'd be no more makeups. I don't know. Okay, let's talk about the next one here. Solvent extraction. Solvent extraction, compared to fractional distillation in this textbook, gets a paragraph. I really feel like this would be a good example where I don't feel like any of you probably can fully get what solvent extraction is just by reading this one paragraph. You probably need to do a little bit outside research to take a look at it. So I did some for you. I just went to Google Images, actually. I found a picture, which really we already have this picture, a picture of fractional distillation. It'll separate things based on how heavy the items are. I just went and found a Google image trying to talk about solvent extraction. And I really feel like a reasonably smart student can just look at the picture and use that to help us figure out what's going on. So here is an example of an organic solvent. And it sure looks like inside the solvent, you've got different types of molecules, two different ones within there, right? Black and green. I don't think it really matters which ones they are, but there's two things inside there, right? And what we've done is we've added an aqueous solvent. And as I look at the solvent right now, it's separated into layers. And there's a word right here that hopefully you guys know, immiscible. Do you guys remember what that word means? It means they don't mix, basically, right? Why would they not mix? Yeah, polar and non-polar. You probably have a polar and a non-polar layer to this, like oil and water. Well, then what they've done is they've shaken and stirred this to allow the molecules to kind of separate and partition throughout the whole solution. Does that make sense? Well, as it finally starts to rebalance itself, again, the polar and the non-polar layers do separate themselves. But this one's kind of cool. What's happened here is that the phases have now settled and separated. And look, the black particles are now on the top, and the green particles are on the bottom. There. That took me all of 30 seconds, by the way, to type in solvent extraction and go look for a photo, so that now I have a bit of an idea of what solvent extraction looks like. Because, like I pointed out here, this textbook page on solvent extraction, I mean, really, all you have to go with here is several of these physical processes are solvent extraction. A solvent is added to selectively dissolve and remove an impurity. That's all you got. You know what I mean? So I feel like this would be a good example where if you want to know more, I want to empower you that you have this information at your fingertips. All you have to do is, use the internet, watch a YouTube video, find a Google picture. I really do feel like this one picture that I found online is probably enough to help further your understanding of solvent extraction. Both of these first two processes here, where are they, are physical processes, where you're using some sort of physical property to separate compounds out. Okay. Are we chemically changing them in either of these two things? No, we're just removing, like you're separating them. You guys remember the term homogeneous and heterogeneous, or homogeneous, heterogeneous mixtures? Basically, we're just separating mixtures here. The next couple of terms here are all chemical processes, where we're actually going to literally change the type of chemicals through a reaction. And, I mean, your textbook, again, does a pretty good job, if you can find the pages. Where is it here? Where then it'll go on and it'll even say, so where was it? Chemical processes in oil refining. And so, I mean, it'll go through and talk about cracking. And, I mean, you can probably read a little bit here and go, okay, well, cracking is a chemical process in which large molecules are broken down to small molecules. Honestly, if you know that, you're going to answer the diploma question. But I think this is more of a give a man a fish versus teach a man a fish concept. I've not told you the answer to the diploma question. If they ask what cracking is, take big molecules, make them smaller. Problem solved, right? Do you really understand what's happening, though? No, we got to dig deeper. You know what I mean? So, I mean, they give in a couple of bolded or italicized words here, thermal cracking and catalytic cracking, and they give one example. So let me see whether I can add some more to this concept here. Because really, actually, no, there's two examples here, but this is hydrocracking. But I don't know if that's enough. So I did the exact same thing. I just did some Google image searching to try to talk about what cracking might look like. And this was what I found for the first one here. Hexane turns into butane and ethene. Essentially, a big molecule right here, this is a large molecule, 6 in a row, has been broken up into a group of 4 and a group of 2. What's unique about how this works is that this 4 right here is still all single bonds, but this one right here is a double bond. Why? Well, okay, so you keep these carbons right here. So let's say you cleave this thing in half right here, right? Can you just leave this carbon right here uncapped? Well, no, we need to have another hydrogen. So it looks like what's happening here is this hydrogen right here is actually attaching itself in that location right here. And now you're left with this molecule right here. Well, that guy's also got a problem because this carbon right here doesn't have enough bonds. So it looks like what's happening in a fairly complicated process is this hydrogen is maybe shifting over one, and you put a double bond there instead. Well, I was doing some research yesterday, and this is where sometimes even as a teacher, like I'm a chemist by trade, like this is what I learned. Going to Wikipedia is not a bad idea. Oh, I just typed in cracking. And first article that comes up is cracking for chemistry. Okay, awesome. And I gotta be honest, you gotta wade through the crap. Like Wikipedia is a great resource for you to learn stuff. But is every single thing in here gonna be important to us? No, not by any means, right? So you gotta learn to be able to read through here and go, okay, well, what's relevant here? So as I gloss through, cracking is the breakdown of a larger alkane into smaller, more useful alkanes and alkenes. I think I just saw that in the picture, right? You had single bonded stuff breaking up into single bonded stuff, but also a double bond. Get a bit of a picture to go with it. As I kind of glossed through this, I was reading this yesterday. Okay, history and patents, probably not relevant. The chemistry behind it, okay, kind of cool. You can look at this. And I mean, even this right here, I recognize right off the bat, this is probably more info than we need. Here we've got a molecule that somehow is breaking up into pieces. Now, I happen to know what this dot right here means because I went to university. Basically, this means that you take a carbon, 3 hydrogens. So it used to be this molecule right here, and we cleave it in half. What ends up happening is you have your hydrogen here, your hydrogen here, your hydrogen here, and you get a single electron. That's what that dot refers to. Is this molecule right here full? No, we really need a bond here, not a single electron, because we've really just cleaved this thing in half. So I have a little more context just because I know what that means. That's what this little dot right here means. And then as I read, now I'm starting to get a little bit lost, because then there's a second step where one of those things reacts with another and somehow makes a methane. And now there's like a branch, but there's another dot on the end. And then it looks like this guy right here is doing another reaction, forming a hydrogen. And as I read through, now there's even another reaction happening here. And then there's another reaction happening here. And at this point, I started to recognize, okay, this is probably above the level of what we need for Chem 3. You know what I mean? But this is the process I went through, where I had to kind of glean through and figure out, well, what is really relevant and what's not. And then eventually I found a picture, which is that picture that I showed you right here. I said, you know what, I think this is probably sufficient. Because although I now recognize that this arrow is, and there's more to it than that, it's not just that this one molecule broke up into those pieces. It was probably like a 5-step process. This is probably all we need to know. Long chain breaks up, and by the time you're done, you have single bonds, and you probably have double bonds too. And I found a second picture, same thing. It looks like this thing got cleaved off right here. So we've got a 5-in-a-row chain, and this guy looks like it put a double bond there so that maybe this hydrogen could slide over into this spot, and this hydrogen maybe slides over to that spot. Is it more complicated than that? Yeah, for sure. But do we need to know that for this? Okay, so that's cracking in a nutshell. Now, there were 2 different kinds of cracking, though, when you read the textbook. One was thermal cracking, and basically it just means heat it up really hot. But you know what? It's actually the same thing as fractional distillation. I didn't realize this until I watched the YouTube video. You have to remove all the oxygen, though. Because again, if you heat it up in the presence of oxygen, it may combust instead. So we don't want it to combust. We just want it to somehow crack the molecule into pieces. Your textbook actually shows an example of something right here that I'd like to talk a bit about. They give one example right here about what a typical reaction looks like. Here they've got 17 carbons in a row, then 36 hydrogens, and they break it up into a group of 9, a group of 7, and a single carbon. And this actually kind of explains why here they mention how it's kind of a dirty process. It makes solid carbon, solid coke, which is a very dirty sort of chemical. Let me see if I can show you how this formula works here. So another type of cracking might look like this. You have all these carbons in a row. And rather than cleaving it in, say, one place, we're actually going to break it in two places. I'm going to break this guy right here and right here. Well, now my group of 6 is a group of 3. You see how this guy right here, he's missing a bond right there, right? Well, what he's going to do is he's going to steal this hydrogen and put that hydrogen right there. So that hydrogen's up. Well, this group of 2 right here, it's looking pretty good so far, except we're missing a bond over here. Well, what does it do? We're just going to steal this hydrogen over here, that hydrogen right there. So this guy's out. Well, what's the byproduct that's left over? Just a single carbon atom. So this is another example of cracking, which, I mean, I didn't find on the Wikipedia, but I did find on the textbook, where we've now taken a molecule that was 6 in a row, and we found a way to break it up into a 3 in a row, a 1, and a 2 in a row. Does that make sense? So that covers thermal cracking and catalytic cracking, but then it talks a bit about hydrocracking. Well, again, it's the same concept. I mean, cracking essentially is take big molecules and make them smaller, but this one's got a slightly different mechanism to it. Anyone catch how that mechanism works? What makes hydrocracking different? It removes the solid carbon. You don't actually have that solid carbon anymore. Why? Yeah, because hydrocracking means that you're adding hydrogen. So imagine that it's this molecule again here. Okay, this time around, let's just cleave off just right here. We're breaking the pieces. So now you got a group of 3, and looks like a group of 3. But I mean, we're lacking something right there. Like this doesn't fit, right? Well, the way hydrocracking works is this is really clever. Add some hydrogen gas. Well, if you add hydrogen gas, it means you've got hydrogen attached to hydrogen. One of these hydrogens can go take that spot. The other hydrogen takes that spot. Well, this is brilliant. Rather than having this dirty process where you get a lot of that solid coke individual carbons, now we don't have that. Now we've got just 2 different pieces, and they're both completely saturated compounds. Clever, right? So there's a little bit more on the first 3. What did your textbook say about catalytic reforming? Yeah, it converts something into an aromatic is essentially the concept. I found a picture. I mean, I did the same thing. I just typed in a Google search to try to look for catalytic reforming because I was hoping to try to get a picture to help explain things. And hopefully this one makes sense. Here we've got a compound where, does this one have a benzene to it? I'd say no. This looks like it is a methyl cyclohexane. Cyclohexane because we have 6 in the circle and a methyl off of it. No, I don't need to see these. I actually don't know why that's a CH3 though, but probably as a typo it should be a CH2. Anyways, what it looks like's happened here is they found a way then to rip off one of these hydrogens and one of these hydrogens, rip off one of these hydrogens, one of these hydrogens, rip off one of these hydrogens, one of these hydrogens, and found a way to turn it into a benzene ring, but in the process, they pulled some hydrogen off of this thing. Does that make sense? And so you found a way to take something that wasn't aromatic and make it aromatic. Here's another picture I found. You've got yourself a methylcyclopentane, so a group of 5 in a row, and it has a CH3 sitting on the end. And somehow, I mean, there's probably intricate steps in between, but somehow we found a way to make this a group of 5 plus 1 more turn into a benzene ring, and in the process, we pull off some hydrogen. So, I mean, that's at its core what catalytic reforming is, finding a way to make a benzene ring out of things. The next 3 probably can all go together: hydrogenation, dehydrogenation, and dehydration. And I mean, essentially, they're all now refining processes where now that you have your hydrocarbons, you want to do something cool with them. This is actually the third topic we're going to start branching into next week. Remember how I told you I had 3 main goals? The first one was that hopefully you'll appreciate that we use organics everywhere. The second one is how to name them. Well, the third topic, which we'll get to, is some of the reactions we can do. And these 3 are some of the reactions that take place. Here's hydrogenation. And again, I just found a Google picture to help with illustrating things. What is hydrogenation doing? Adding hydrogen to a compound. Here's a double bonded molecule. Add some hydrogen. Now it's saturated. That makes sense? We filled in the open spots with hydrogen. That's what hydrogenation does. Technically, this is called an addition reaction, which we'll use that term in a week or so. But what we've basically done is we've taken this hydrogen, we've added 1 hydrogen here, and just double bond. That's hydrogenation. In a way, doesn't that make hydrocracking a form of hydrogenation? You're adding hydrogen to molecules. Here's another one. Only this is the opposite. This is dehydrogenation. Well, if hydrogenation is putting hydrogens on a molecule, dehydrogenation is taking hydrogens off a molecule. This is actually that catalytic reforming again. Here we've got our molecule, we've turned it into a benzene ring, but in the process we've ripped off some hydrogen. That is dehydrogenation. We actually have another name for this as well. This is called an elimination reaction when we talk about this in a week or so. Because you're eliminating off hydrogens. Well, take a leak then. What would dehydrogenation then be? Hang on, was it dehydrogenation? Dehydration, that's what it was, dehydration. What do you guys know about dehydration otherwise? Well, it's where you're thirsty, you have no water. It's the removal of water, right? Now, we haven't learned this molecule yet. We will soon. This is called ethanol. See how I have an OH and an H right here? If you were to find a way to rip an OH and an H collectively off a molecule, you'd be ripping off not just H2 gas, but ripping off water. That is dehydration, removing the water from a molecule. And in the process, we go from a saturated molecule to an unsaturated molecule because now there's double bonds. Does that make sense? Here's another picture I found online. Here we have a molecule that, this is not quite a benzene ring. It looks like it's a cyclo with 2 double bonds, a couple of different functional groups kind of sitting around the edges. And, I mean, you guys hopefully know what this on top of the arrow means. What does it mean if something's on top of an arrow? It's a catalyst, yeah. So it looks like it requires a catalyst, and it's going to subtract off of water. So it looks like right about here, this water has been pulled off. And instead what's happened is maybe this guy is shifted over 1 somehow, and we've gotten ourselves a benzene ring. I imagine this is not a 1-step process. It's probably 3 or 4 steps. But another word on there was something called alkylation. And I don't know that there was really a lot written in your textbook about it. What did you guys write down about alkylation? What'd you write? Okay. So makes an isomer, but of what though? Like, what's the point? Anybody else want to volunteer with that? You guys are so quiet all sitting. Okay, so you're kind of blurring into octane numbers. That's all it basically gave them. It improves the quality of gasoline. Okay. So let's talk about that for a bit then. What does branched mean? Yeah, you have more groups. Here's a very long straight molecule. Well, if we can find a way to add some branches to it, that changes the molecule. Let's blur into octane number, because this is a bit of a conversation about the fuel you put in your car. There was a blurb in your textbook talking about octane number. Basically, the higher the octane number, the better the quality of the gasoline. That's the nuts and bolts of it. My question, though, is why? Why is it better? Did you guys catch that? What was that? Okay, but why does it burn cleaner?
There's larger molecules in the top, so it comes spontaneously combusting before.
There we go. You got that. Okay, so we don't want our gasoline to burn out of turn. The way that your engine works is that there's a piston that goes up and down regularly, right? I mean, if you've seen an internal combustion engine in science somewhere before, there's like the intake, the exhaust stroke. There's 4 actual different mechanisms where the piston goes up and down. And what you'd like to do is you'd like to control the explosions so that the gas combusts when you want it to combust. Because if it combusts too soon or too late, then it's inefficient. Does that make sense? Well, gasoline might spontaneously combust if the pressure is high enough, and it usually does that if the molecules happen to be just unbranched. If they're just like this molecule I would have originally drawn right here, this molecule right here will sometimes combust when we don't want it to. We've discovered that branched molecules actually, they don't have that property. So when you guys buy a higher grade of gasoline, like if you buy 91 or 93 rather than 87, you're actually just buying a molecule that has more branches on it. That's all. So then the question is, through the process of alkylation, how do you do this? Okay. Actually, there's a question on one of your tests you guys are going to get, where it shows you 2 molecules, and it shows you them merging together, and you have to figure out what they're going to predict. Kind of like this picture I have right here. Let me talk through this picture here. This is what I found when I googled alkylation. Here you've got a molecule, and here you've got another molecule, and it looks like you've got an H plus over top of the arrow, meaning that H plus is probably the catalyst. And as I look at this, it appears that this piece right here is still kind of sitting there right about here. Does that make sense? With one exception. This is HC3, CH, CH3, CH3, but here there's a CH2. Well, why did that change? Well, I think we need to take off a hydrogen, because really what's happening here is if you used to have 3 hydrogens here, we have to remove one of the hydrogens so that it can keep bonding to something else. Does that make sense? So one of the hydrogens has now been pulled off this molecule. This molecule here, right here with the double bond, I believe it's actually this guy right here that's attaching. And so that's where this CH happens right here. This CH3 is down here. I don't know why they wrote it quite like that.
No, the CH is up there, and then the CH2 gets the molecule like this.
And, well, it doesn't really matter which one goes where, right? Because this CH2 right here is going to become a CH3, or either one of these 2, right? And you know that extra hydrogen that I had to rip off? It's going right there, I guess. Or it's going right here. Essentially, this piece right here is attaching to that spot. This is alkylation. We've now made a molecule, and this molecule is very branchy. You know what I mean? Like there's a 1, 2, 3, 4, 5 in a row. But it looks like there's a methyl group here and a methyl group right here. So based on what we understand about combustion, this will not auto-combust just due to high pressure, which is why it's more valuable to use in our cars. That makes sense? Okay. Okay, at the end of the day, you're probably going to get no more than 1 question on this topic. Like, it's not common, and you need to have a very cursory level knowledge of these sorts of terms. But what I do want to kind of put a bug in your ear and just make you think about is how to look information up either in a textbook or on the internet. You can learn so much nowadays just by watching a YouTube video on things. Speaking of which, you can learn a lot by watching my YouTube videos even. Anybody do that? I mean, if you need to rewatch something, watch the YouTube video, right? But I guess I'd like to point out to you that, like, you have all sorts of information at your fingertips. Make sure you use it, you know, and learn how to use it now in high school. Because I promise you, I mean, I'm 30 years old now. The number of times that I need to go research something because I don't know how to do that, like, it happens like weekly, where I have to go find out how to learn how to do something. And having the ability to just learn how to do stuff, I think that's worthwhile. Whether it's me learning how to build Kinsey Ann's Playhouse, blow the sprinklers out, or well, the other day I was going to go play video games with some of my buddies. I haven't played video games in a long time. I didn't know how to play this one, so I watched a YouTube video showing me all the different moves that I like, how to play a video game. I know it sounds kind of silly, but I didn't want to get embarrassed by my friends, so I watched a quick video tutorial showing me all the different buttons on how to play this video game. You can learn how to do pretty much anything nowadays. So I just want to encourage you, start doing that more. Okay, I think I'm done. We'll chat tomorrow, I guess.